Module 1 is a review of heat transfer fundamentals. It's broken up into 3 lessons. The first lesson is heat transfer modes and basic circuit analogy. So, before we talk about that, it's useful to understand better what heat transfer modes actually are. In block 1.1.1, we're going to look at examples of heat transfer in daily life and also in industrial applications. Prior to doing this, we really need to think about a little bit of what it really is, this discipline of heat transfer. Heat transfer is one of the fundamental areas of mechanical engineering and actually is used in other areas of engineering. Chemical engineers have made large contributions to heat transfer as a research area. Continued work in heat transfer occurs in biomedical engineering, and certainly the transport issues associated with heat transfer are important to researchers in petroleum and geosystems engineering, and applications of heat transfer touch on electrical engineering and material science. For our working definition, we can think about heat transfer as an area within thermal engineering that focuses on transport, exchange, and redistribution of thermal energy. And it's important that we emphasize that it's thermal energy transport that we're particularly interested in. Energy in and of itself is a complex term that really can describe many different ways of quantifying sort of the physics of energy-related issues. And we're specifically targeting thermal energy in this class. So really, in terms of everyday life, there are lots of different things that you might think of as non-technical heat transfer. So we show, for example, someone cooking here. And so in a cooking process, whether it's cooking in one's home or cooking on the industrial scale, oftentimes heat transfer physics and heat transfer processes are extremely important to the process. So cooking is a chemical modification of some material, and that chemical modification is promoted, enhanced by energy exchange in the form of heat. So whether you're cooking with an electrical heating resistance system, or you're cooking with a gas flame, in all cases, high temperatures are required, and there has to be some transfer in an efficient way from the high temperature source to, in some sense, the load. And in this case, the load is the food that's being prepared. And lots of different heat transfer physics are important in these systems. If it's a gas flame system, the heat transfer processes begin with the flame itself, which is a reactive system wherein the fuel and oxidizer, in this case the fuel is typically methane, the oxidizer is air. These react to form hot products of combustion, typically CO2, H2O. And these gases, these high temperature gases, are convected, and so they would be convected out around these ports, and they would be heating up this wok, and there would be conduction through the wok itself to this food material that's being stirred, interestingly, almost in a convective sense. And so as you're moving this food stuff around there, that would be something like a convection process. Sort of continuing in terms of these non-technical heat transfer processes, you look at this torch, and if you think about it, this has to be designed in such a way that the heat transfer processes from the torch itself don't hurt the person who's carrying the torch. And so from a design perspective, one has to minimize the conduction heat transfer from the hot element down through the system. A blacksmith, as an example of another heat transfer expert, will modify materials using a high temperature source, in this case again a flame, and will manipulate this metal once it's been heated. And so while the blacksmith might not understand quantitatively the heat transfer processes associated with this work, by experience and intuition, there's a lot that the blacksmith knows about heat transfer issues. Here we see, for example, that this piece of metal that's being worked on has been turned red, and that red is an indication of the radiation heat transfer that's occurring from the metal. We'll talk about radiative heat transfer and the issues associated with that. Here we're looking at a hairdresser blow drying a woman's hair. And again, it's a heat and mass transfer process in the sense that there's electrical power that's being transmitted to the hair dryer and the blow dryer. Elements are heated up within it. There's force flow, convection that goes through the blow dryer, and this convectively interacts with the heating elements. A hot air jet comes out of that, and that hot air jet is going to affect the mass transfer process, an evaporative mass transfer process on this person's hair in the drying process. So, interestingly enough, even in these non-technical systems, there are relatively complex heat transfer physics that are required to actually quantify and understand what's going on in these systems. As we move on and think about the details of where these technical issues arise, we look at, for example, whether it's this blacksmith's forging and heat treating process on a piece of metal, as shown here, or in a cooking process, as shown here. So here we again have the blacksmith and metalworking as compared to the cooking process. And I want to emphasize that in both of these processes, quite a bit of work is required to be able to provide quantitative descriptions of the processes. So first, we'll think about this cooking process, and let me make sure that we're clear that the cooking process is not the blacksmith metalworking. But so in this cooking process, from a flame, it looks like here the cooking is taking place perhaps outdoors and over a campfire or some sort of wooden elements. And the first thing that happens is that we have to transfer heat from our fuel, the thing that costs. So the fuel is the thing that costs here, and we want to try to, as efficiently as possible, transfer that heat into our load. And so this is the fuel / source. And there are many ways that this fuel and source generate heat to heat up our load. Again, this is a chemical process that would be discussed in a combustion or fire class, this combination of fuel and oxidizer to create this hot environment that's going to be used to actually promote and to cook this food, or in this case, to boil the water. But what's interesting about this is that there are different ways in which this hot environment interacts with this pot. And so shown here, for example, is radiative transfer, and that radiation is primarily from the orange flames here. So these flames are shown as orange. What I talk about, for example, in a combustion class is that the orange glow of a flame is actually the soot particles within it. So there are solid carbon particles inside this flame. So these solid carbon particles, not unlike the smoke that you see in a candle flame, when they're heated to very high temperatures, they look a lot like what this piece of metal looks like. They start to glow orange or glow red. And so what we're seeing really is these soot particles, and they are doing something called broadband radiation. So these things are radiating in this high temperature flame environment. And so that's one thing that has, from a heat transfer perspective, that affects the system. Typically, that's not the dominant heat transfer mechanism, for example, this cooking system. What's the dominant mechanism is the convective flow, or sometimes direct contact in terms of conduction. But in this case, it might be the convective flow. So the hot gases have a much lower density than the surrounding gases around them. And so we set up this convection current where these hot gases rise, and these hot gases transfer heat as they flow over this pot to the pot itself. And so we get convection and radiation as heat transfer processes from this fuel burning process to this pot. Within the pot itself, as you see, we have convection processes and conduction processes. The first process really is a conduction process, and that's a conduction process across this very thin piece of metal that is the pan. So if I expand the pan here, and I have these hot gases, let me see if I can shift colors here. So I have these hot gases coming around this pan. So these represent the flow of it. There's got to be some sort of transfer process across here. And so there's heat that is transferred across a resistance, an impediment to this heat transfer, which is the pot itself. And so this is a conduction process that first occurs across the pan. And then once this heat crosses the pan, it starts to heat up the water inside the pan. Initially, as it heats it up, it sets up what you might call, again, a natural convection circuit within it. And so you see these flows in here. So what this represents is, again, relatively low density, high temperature liquid that rises and transfers heat to the locations where it had been colder. There's a phase change process that also occurs. We know this to be called boiling. Boiling is within the convective heat transfer sort of area of research. It's connected intimately. It's a phase change process, so it's sometimes called phase change heat transfer. But boiling is an important industrial heat transfer application, and obviously it's important in terms of cooking and sometimes making a good cup of tea or whatever hot drink. And so again, these are the processes that are occurring, and of course from a safety perspective, conduction is important in terms of minimizing the hazard of handling this hot pot, and so design issues have to take that into consideration. So we've qualitatively discussed some of the issues that surround this relatively simple problem, and then I'm going to talk a little bit about this metalworking process shown here on the left in terms of perhaps more quantitative issues. We don't have the tools at this point to really understand this. Later on, as we go through the semester, you will be able to understand all the issues that are associated with this problem. So if one wanted to understand what the temperature distribution is, so maybe I wanted to know what the temperatures are in a piece of metal because either the material properties are related to that temperature distribution, or there's some hazard or risk associated with it. So the reasons to understand the temperature, could be materials considerations, or it could be from a safety perspective, so someone has to handle this, or it could be for any number of other reasons that one might want to know what the temperature is. And so we'll find out within the next few lessons how to construct an equation that would enable us to find what the temperature distribution is. And we'll show that there are several types of terms that could come about for this. We're doing a relatively simple approximation in this particular problem called the fin approximation. We'll talk more about what a fin is again as we move forward. But what you see is that there are transient terms which mean that these are time-dependent terms. These are time-dependent factors, and that there are terms that take into account conduction. We'll find out that this K parameter is called the thermal conductivity, that it is an intrinsic material property, and that it helps us understand how heat is transferred in these conduction processes. We'll see that there's an empirical law called Newton's law of cooling that tells us how heat is transferred from a solid to a bulk fluid surrounding the solid, and that there is another law called the Stefan-Boltzmann law that takes into account how radiative heat is lost from a solid and to the surroundings. And so this is a complicated, and let's make sure that we understand what kind of equation this is. This is a complicated partial differential equation. And equations like this, EQN being an equation, are oftentimes solved numerically, particularly when they have nonlinearities like this radiation term. So what do I mean by nonlinearity? Nonlinearity means that this equation has a dependent variable that's not just in terms of the first power, for example, of temperature. So all these t's are really t to the first power, but also in terms of higher order terms like this fourth power of the temperature. And so when we have nonlinear partial differential equations like this, there are not oftentimes simple analytical solutions for these, and we have to solve this numerically. Again, what this would give us if we solve this problem would be the temperature distribution. It would tell us what the temperature is at different values of x, where x is some axial length on this poker. So if we looked at this hot piece of metal and we said that there's a coordinate system x that comes off of it, we would know, for example, that perhaps this thing is 800 degrees on one end of it and might cool down to, for example, 100 degrees on the other end, and we'll know what the whole distribution of temperature along this would be. So the benefit of our having tools to quantitatively evaluate systems like that is extremely powerful. So we've talked about these non-technical heat transfer systems, but obviously heat transfer is extremely important in industrial systems and industrial applications. So one area of particular interest is in electronics and electronics cooling. So in electronics cooling systems, and this can be anything from your mobile phone to a server, etc. In all these cases, there are material limitations associated with the operational temperatures of the fundamental components of these, which are oftentimes the CPUs. So there are materials constraints that really are equivalent to thermal constraints. So the temperature distribution within these systems is motivation to think about heat transfer consequences of their operation. And so one of the things that has been done for years in terms of keeping chips cool is to incorporate augmented heat transfer area surfaces called fins to increase the heat transfer rate away from this hot spot where it's oftentimes joule heating inside there that causes these high temperature regions. And so by adding surface area to increase the heat transfer area, we can maintain or reduce the temperatures to some temperature below a critical operating temperature for these systems. One of the largest areas for energy utilization in the U.S. is in materials processing of metals. And heat transfer is an essential part of the materials processing systems. These could be anywhere from forging type furnaces. So, prior to forging, you have to heat up some billets and samples. It could be in heat treating furnaces. So to get some sort of required material property for already, somewhat finished parts, you might have to go through a heat treating process. In all these cases, heat transfer is critical. And when you think about the energy inefficiency that can perhaps occur, and this is, here we're really looking at an inefficient system in some sense because we're burning fuel, and that fuel is creating these high temperature gases, but we're losing high temperature gases convectively out of the furnace. And so, there are issues in terms of how do we better use these high temperature gases for not only perhaps the primary issue, which might be the heat treating or the forging or whatever the materials processing issue is, but also in terms of, in some sense, the lower quality gases that might be escaping. And in these systems, again, you see that a lot of the heat transfer processes are radiative heat transfer processes. We're talking about very high temperature systems here. And in very high temperature systems, radiation oftentimes is the dominant mode of heat transfer, particularly when there are large length scales associated with the systems. So we're going to have to understand better what happens in these types of systems. Interestingly, heat exchangers are one of the most important heat transfer technologies that we use in industrial systems. And these are just a few different types of heat exchangers. We routinely use heat exchangers in everyday life. I think that, if you're in a car, you know that the radiator in a car is a heat exchanger. There are heat exchangers in various components for sort of any kind of industrial food processing, for different types of petrochemical industry systems. Heat exchangers are ubiquitous and are extremely important for the process industry. And again, there are many different types. We're going to do basic analysis of heat exchangers to understand what they do and how they function. If you think about it, the basic heat exchanger really might be something, you might think about a co-flow heat exchanger system. So let's think about a channel where the top channel of the channel is a well-insulated boundary. In heat transfer language, you know that this is the idealization of very well-insulated is called an adiabatic surface. So we may have this adiabatic top surface here. Imagine that we have an adiabatic bottom surface also. And we have a thin conducting element that is used to transfer heat between these two, that breaks up this flow channel. And so imagine we have a hot fluid on top, initially hot, an initially cold fluid on the bottom, and these flow into this system. So we have a flow into this system, and certainly we would expect that there's going to be heat transfer across it. And this is an important issue in processing, and understanding what happens in this system is useful and, as I mentioned, industrially relevant. Another very important heat transfer system is the gas turbine. So gas turbines are used in a lot of different applications. They're used in propulsion. So if you're flying from one place to another, you're relying on gas turbine technology to power that the engine on the plane. Gas turbines are extremely important in power generation, and not surprisingly, in all these different applications, one of the critical issues for efficient use is increased temperature. So the higher temperature, the gas turbine operates on something called the Brayton cycle. And in the Brayton cycle, this is again a thermodynamic cycle, the hotter you get the working fluid, the more efficient the system becomes. But not surprisingly, there are constraints, and those constraints are material constraints. So, you know, this is a thread that has run through some of the discussion that we're going through, is that there are thermal materials constraints that seem to show up in a lot of different settings. In some respect, the heat transfer discipline really is a direct offshoot of materials engineering. So, you know, if materials, in some sense, you know, had no limitations in terms of what temperatures they could operate at, there would be far fewer heat transfer problems of interest, because, you know, if I don't have to worry about what temperature a particular material starts to break down or degrade, then why do I really worry about the heat transfer issues? But of course, that's, you know, in some sense against all laws of physics, that degradation shouldn't occur, and it just happens that high temperatures accelerate degradation and affect materials in a significant way. So in the gas turbine area, one of the issues is that we see conduction. So you have a high temperature gas that's flowing. Let's see if we can switch to red here. So we have a high temperature gas that's flowing across this turbine blade. So inside the gas turbine, what you have to recognize is that the gas turbine is broken up into a compressor section and a turbine section. And in the turbine section, you're using hot gases to blow over the turbine blades to spin them, and that's where you're getting your power generation from. So there's a combustion process that occurs where energy is added to the working fluid, and this working fluid again turns these turbine blades. So you have this high temperature flow over these turbine vanes, and we don't want this high temperature flow to necessarily heat up the turbine blades. That's not what we're trying to accomplish. In some sense, we really have just used this high temperature to create, again, this high velocity, high energy flow that we're going to extract work from. So to protect the turbine blades, one of the strategies that's used is providing bypass air or cooling air that goes through the vanes themselves and protects the vanes from this high temperature flow. And so this cooling strategy is something that we're going to discuss in more detail as we move forward, and it's oftentimes called a film cooling process. So industrially, this is an important issue for gas turbines, and this is what we're showing here. So, they talk about sort of shower head regions and different parts of this vane where the flow comes through and creates really a cool layer, cool sheath around the blade to protect it from this, again, high temperature environment. So convection is extremely important to these systems. These are turbulent flow systems. We'll talk about what turbulence means and what the issues are in these types of systems. And then conduction also is important. And so, this is not an adiabatic material, so there is heat transfer that goes through the solid, and it's important to be able to characterize and analyze that. So we've talked about heat transfer in everyday life, and we've talked about some of the issues associated with it in industrial settings. What's really next is that we want to talk about how heat transfer and thermodynamics are related. So I'd like you to think about how are heat transfer and thermodynamics related, and how are heat transfer and thermodynamics different. Being able to think about these questions will really lead us through the next section of discussion.